Hey guys, welcome to the third gas law that we're learning about. It's called Gay-Lussac's law, and this is between temperature and pressure. You'll need your notes, your pen and paper, your Unit 3 Section 2 packet, and your calculator. So here we're going to look at what happens between pressure and temperature of gases, and then we're going to calculate what happens when we change the temperature. So what happens with the pressure when we change the temperature. So let's take a look at the PhET simulation, and you guys can tell me what ends up happening. I know that I'm just dealing with pressure and temperature here, so I'm going to keep volume constant. So the container size should stay the same, and we'll add in some particles into here. Okay. So the pressure is around 0.7 atm, and the temperature is at around 300 Kelvin, so it's stabilizing. Okay, I'm going to add in some heat. So I know that the temperature is increasing, the average kinetic energy of the particles is increasing, and my pressure is also increasing. So as my temperature increases, my pressure increases. In fact, let's take a look. Ooh, we busted the lid there. All those gas particles are leaving the container because the pressure built up was too high for the strength of the container. Alright, so let's start that again. This time, we'll see what happens to the pressure as we decrease the temperature. So my temperature is around 300 Kelvin. My pressure is around 0.7 atm. Now I'm going to make this colder. So my Kelvin temperature is decreasing. Notice the particles are moving a lot slower. The average kinetic energy is decreasing. And my pressure is decreasing as well. So as I decreased my temperature, my pressure also decreased as well. Alright, so I'll get rid of that. And we'll go back to that PowerPoint. So you guys can go ahead and tell me what happens between pressure and temperature. This is called Gay-Lussac's law. So when we keep volume constant, meaning we don't change what the volume is, the temperature, as the temperature of the sample decreases, the pressure of the gases decrease. Conversely, as we increase the temperature, the pressure increases. So pressure and temperature are directly proportional, and we can show that by saying P is proportional to T. So our formula is P1 over T1 is equal to P2 over T2. And our graph kind of looks like our Charles law graph. It increases proportionally, and the temperature is on the x-axis, the pressure is on the y-axis, and you see that straight line going right on up. Alright, so let's also take a look at this. Here we have a Florence flask inside two different conditions. On the left-hand side, it's in an ice bath. On the right-hand side, it's in boiling water. So left-hand side's really cold, right-hand side's really hot. Notice we have the same number of particles in each one. This container is capped. There's a lid to it, so we actually don't change the number of gas particles. We'll take a look here. We have it says to the manometer. Manometer is just a way for us to determine what the pressure is. So the pressure in the ice bath was 1 atm. When we increase the temperature, we increase the average kinetic energy, and the pressure also increases as well. So let's take a look at some of the calculations. This is also in your packet. So the table shows data for a glass bottle in 4 locations. The atmospheric pressure stays unchanged at 1 atm, but the temperature changes. Complete the table. So here I have air outside of the bottle, and on the right-hand side, I have air inside of the bottle. And so we'll talk about the outside versus the inside. And we want to know what happens to the pressure over temperature, so where that little k value would be. Notice that the volume, and actually I'm going to label these 1, 2, 3, 4. These are 4 different trials, 4 different experiments that are going on. So notice in each of them the volume stays the same, so we're not even going to deal with the volume. We'll notice with the air on the outside, air on the outside, the pressure stays the same, so we actually don't even need to deal with this. We're more focused in on what happens inside of the container. So as the temperature increased, it went from 200 to 400, from experiments 1 to 4. The pressure also increased from 0.67 atm to 1.34 atm. So here we need to figure out what little k is equal to. And little k was, again, that little constant that we talked about in Charles' law. So little k is P over T. So little k is the pressure over temperature. So if I use experiment 1, I had 0.67 atm over my temperature, which was 200 K. And from there I get 0.00335. That's supposed to be 35. And these units, so if I have pressure on the top, it's atm on the top. Temperature's on the bottom, so that's Kelvin on the bottom. Alright, we'll do the same thing for experiment 2. I know I want pressure on the top, 0.80 atm. On the bottom is 238 Kelvin. And that's about 0.0036 with proper sig figs, 336 with proper sig figs. Experiment 3 is, let's see, 1.0 atm over 298 Kelvin. So with proper sig figs, it's 0.00336 as well. Right? And I don't have enough space here, but make sure you write down what the fourth experiment would be. It's 1.34 atm over 400 Kelvin, and that's 0.00335. If I haven't done this already in your notebook, make sure that you add some decimal points from the 200K and 400K, just so that your sig figs make sense. You would normally never do this unless I tell you to, so if you hadn't already and you were confused about the sig figs, that's why they each have 3 sig figs, okay? But again, don't do that on your own. Ask me if there's a question on a test or a quiz or something, if I meant to put a decimal point there, and most likely I did mean to do it, and I just forgot. So let's go through, plot the pressure versus the temperature, and use a best fit line to connect the points. So we'll look at the pressure scale, that's on the y-axis, and that's an atm. So each of the major lines is increasing by 0.5, so each of these tiny little lines increase by 0.1. So that's 0.1, 0.2, 0.3, 0.4. We'll go up 0.6, 0.7, 0.8, 0.9, and label the rest. 1.1, 1.2, 1.3, and 1.4. And that's all those little lines. Whenever you have a graph, make sure you do this. I expect to see this on all your graphs, okay? As best as you can squeeze them in. Your x-axis is your temperature in Kelvin, so we have 1, 2, 3, 4 little lines in between from 0 to 100. So know that increases by 20. So 20, 40, 60, that one would be 80. Then it goes up to 100, so that's 120, and I'll do 140. 160 is that little line right in the middle. Then I have 180 up to 200, and then so on. You'll have an easier time writing this on your paper than I do on this screen. So go ahead and pause me and fill in those little dots. Okay, so hopefully you paused me and went ahead and plugged in those values. And didn't want to make sure that you saw this. You're probably asking, what data do I put in? Hopefully you saw that it says inside a glass bottle, so that's what we meant. So your graph should hopefully look better than mine, because mine's with a stylus, yours is with a pen. So let's take a look and see, what is the pressure if the temperature is 300 Kelvin, or K? So we'll go to 300, and then go across. Let's see. So let's see, if my lines lined up a little bit better, you might end up having like 0.90 atm. Okay, so we'll kind of sketch that line a little bit better. There we go. Alright, so let's take a look at one of the problems we might give you in class. Determine the pressure change when a constant volume of gas at 1.00 atm is heated from 20 degrees Celsius to 30 degrees Celsius. So let's highlight the important information. We know gas is the volume is constant. We have 1 atm, and it goes from 20 to 30 degrees Celsius. Alright, so we know that when it says atm, that's pressure, that's P1. And what's the pressure change? You can just give me what the P2 would be over there. This is T1 and T2. So the first pressure is 1.00 atm. That first temperature is 20.0 degrees Celsius, but hopefully you remember that we don't do degrees Celsius, we only do Kelvin. so that's 293 Kelvin. Your P2 is unknown, that's your X, and that will be an ATM because your P1 is an ATM. And your T2 is 30.0 degrees Celsius, and that's 303 Kelvin. So we have our equation, P1 over T1 is equal to P2 over T2. We're trying to solve for P2, so let's get P2 by itself. Let's move that T2 up. So P1 T2 over T1, sorry, that's all equal to P2. Let's plug in our values. We have 1.00 ATM. I'm putting in my units so I know what can cancel at the end. T2 is 303 Kelvin over T1, which is 293 Kelvin. Cancel out any units. I can get rid of Kelvin, which is good because I want pressure at the end. Let's figure out the number of sig figs while we're here. This has 3, this has 3, and that has 3. Alright, so my final answer will have 3 sig figs. That ends up being 1.03 ATM. And just in case you're curious how I did this, I did 1 times 3 over 3, but obviously 1 times anything is itself, so I did 303 divided by, because that's what my fraction means, 293 Kelvin, or 293. So to summarize, Gay-Lussac's law deals with pressure and temperature, and they are both proportional to one another. The equation is P1 over T1 is equal to P2 over T2. And when you look at the graph, we have temperature on the x-axis, pressure on the y-axis, and it goes up linearly. And it's a direct relationship between the two. So if you guys need any help, please let me know. Take care. Bye.